All right, so we're ready to finally kind of dive into things here and learn our first inference procedure on slope. It is called a t-interval for the slope, or I like to call it a linear regression t-interval for slope. For slope or for beta. But you don't need to have the linear regression in front of it. So when the conditions are met, our confidence intervals are always our stat plus or minus our crit value times the standard deviation of the stat. So that's just what, so our statistic is our slope. So there's our sample slope plus or minus our t-crit, because this is a t-model, because we're estimating our standard deviation. We got a standard error times the standard error of our slope. Here's the formula to calculate that, but usually you're going to get that from the computer output. That's it. That's how we calculate confidence intervals. This is no different. The only thing you got to be careful about is with the t-distribution, this has got a degrees of freedom n minus 2. So why n minus 2? Well, the theoretical answer is complicated, but you can think of it this way, very informally, that when you use a sample size of 30 to construct the least squares regression line, 2 points kind of determine your line. This is a little bit of a backwards way of thinking about it, but 2 points kind of determine your line, and then you have the freedom of choice for the other 28 points around it. More accurate, I don't know. Any explanation I give you is going to be kind of wishy-washy anyway, but basically you have a line determined. You got 28 points of freedom that you can choose, and then those last two need to be determined, one to lock in the y-intercept and one to lock in the slope. Whatever. Long story short, you don't need to know why that is, but whenever you're estimating the slope and the y-intercept, you lose 2 degrees of freedom, okay? All right, so does proximity to the front really matter? So this is the computer output of our example that we did before, where we had all of this row data here. So now, and I believe we had a sample of 30 subjects in this study. Let's pretend we don't. So on the AP test, you're not going to have to type in those 30 pieces of information in your calculator to run Now, they don't want you to type for 5 minutes in your calculator just to get the info in your calculator. So let's just pretend this is all we have. So use the given information to construct a 90% confidence interval for the slope of the regression line that uses row location to predict exam score. Assume the conditions are met. We actually checked the conditions earlier, so we don't have to check it again. So we're going to run a panic. P beta equals the true. I want to say population slope, but this is an experiment, so the true slope of the least squares regression line that uses row to predict score. I don't like how that doesn't comment on a parameter of interest, but I think I'll fix it in the conclusion. A, assumptions and conditions. Conditions are met. N, name the test. This is a linear regression. Name the procedure, sorry. T interval for slope with degrees of freedom equal to 30 minus 2 or 28 degrees of freedom. All right. Calculate the interval. It's my stat plus or minus the crit value times the standard deviation of your stat. This is B plus or minus T crit times the standard error of B. This is my slope right there, negative 0.926 times my crit value that I actually got to find the crit value by hand. We don't do this very often because normally we have our calculator do all the work for us, but we actually got to find that one by hand. Times the standard error of my slope, which is 0.934. Oops. That's where the t-crit goes, times 0.934. So to find the t-crit value, you got to draw a little t-distribution with 28 degrees of freedom. I want the middle 90% cutoff, so that's 5% on each tail. So if I want this value right here, I'm going to put in 0.05 with 28 degrees of freedom. Menu statistics, distributions, inverse t, so I can put in the area cutoff, the left area cutoff, and 28 degrees of freedom. Gives me 1.70. So then we just put in those values. 926, 934. Negative 0.926 plus 1.7 times 0.934. 934. Enter. Grab that calculation and put a minus right there. So negative 2.51 to positive 0.66. So the slope, the interval for the two slope is somewhere between negative 2.5 and positive 0.66. Okay? Conclusion. We are 90% confident the interval from negative 2.51 to 0.66 points per row is captures the beta, the true slope of least squares regression line that uses row to predict score, and optionally for all kids like the kids in this study. We're talking about a kind of a hypothetical population slope here, where that if you were to ask all kids like the kids in this study and conduct an experiment like the one that we conducted, this is kind of how those experimental slopes could vary. No, I'm sorry. This is where an interval that would capture the true slope of the census. All right, does this interval indicate that sitting in the front row causes scores to be higher? Well, we did run an experiment, so we can prove causation. However, our confidence interval says the relationship could be negative, or it could be positive. Therefore, it could also be zero. Zero's in that interval, and that means it's a one plausible value for the population, or for the parameter slope is zero, meaning there's no relationship. So I'm going to say no, because this interval contains zero, indicating it is plausible that the true slope is zero, and therefore there is no relationship. There is no linear association. Between row and score. So this is saying it's possible that there's really not a relationship at all. Okay? All right, now a significance test for the slope. Let me go over the mechanics of it and then do an example. Actually, I'll do it in a video.